Hello class, and thank you for watching. In topic 1.7, rational functions and end behaviors, we're going to describe the end behaviors of rational functions. So similar to the last lesson, we're looking at a function and trying to describe what's happening in the very far left and very far right. Now, because this is a rational function, it's going to be slightly different in some cases. A rational function, first of all, is the quotient, the division of two polynomial functions. And it looks like this. Make a correction here. There should be a parentheses, not a 9. So a rational function would be the equation y is equal to f of x over g of x, where f and g are both polynomials, and g can never equal to 0. And we'll discuss this, why it can equal to 0, in another lesson. But today, like I said, we're going to focus on the end behaviors. So an example of a rational function would simply be if I get the polynomial function of x squared plus 3x minus 5 and divided by x plus 4, for example, okay? Polynomial on the top, polynomial on the bottom. Now, unlike rational functions, some rational functions end behavior is bounded by a horizontal asymptote. Now, this bounded again means a boundary. So some of these rational functions have a boundary line that the graph again becomes kind of parallel to. They get closer and closer to, but they never actually reach again the coordinate of that horizontal line. And the location of that horizontal boundary line is going to describe again the end behaviors. You're going to see that the end behaviors of that horizontal asymptote tells me again how the far left and far the right of these rational functions are going to behave. Take, for example, this graph right here. This graph right here is the graph of a rational function. So we'll call this right here r of x. So r of x is shown. So this is the name of our rational function. We'll say it just calls that, okay? Let's describe what the end behavior of a rational function is. So we'll first do using arrow notations. So first let's look at what's happening to the y values on the very far left. Well, it's rational by horizontal asymptotes, and the left and right hand behavior are simply getting closer and closer to this boundary line of 2. Now, to describe this using limit notations, we start again by writing the same values as before. So the limit as x approaches to negative infinity means the left side, and the limit as x approaches positive infinity means the right side. Well, both the left and right side are getting closer and closer to the value of 2. So using notations, we would simply say that the limit as x approaches negative infinity of r of x equals 2, and the limit as x approaches positive infinity of r of x also equals 2, because that boundary line, this is describing again the end behaviors. Let's take now another example. For this example, this is another example of a rational function. We'll call it q. So q of x is shown here. And to determine again what's the end behaviors of our function, what is y getting closer to on the very far left and very far right? Well, we just simply have to identify where the boundary line is. And right here, if we look at this from both the left and the right, they're getting closer and closer to this horizontal line, which is on the x-axis. Well, the x-axis is the y value of 0. So on the left side and the right side, the y values are simply getting closer and closer to 0. So this would be the limit behavior using limit notation. This is the limit notation to describe the end behaviors on the left and on the right. Now, let's go to the next page and let's figure out again what the end behaviors are to these rational functions if we're given the equation to the rational function instead of the graph. Now, obviously, you can just simply graph it using a graphing utility and graph it and see what the end behaviors are. But since portion of your AP test does require you to do things without the calculator, well, let's practice again that for that portion of the test. Now, the end behaviors of a rational function is determined by simply looking at the leading terms of both the numerator and the denominator. So ignoring everything else and only focusing again on the leading terms of both the numerator and denominator, there's going to be 3 cases that result in 3 different type of horizontal isotopes, or isotopes, okay? Because the first 2 are horizontal, the other one is not a horizontal isotope, this case 3. Let's look at the first case. Case 1 is that for the leading terms for both the numerator and denominator, the leading terms have the same degree. So that means that this number here is equal to that number there. In that occurrence, when those numbers are the same, the horizontal isotope is always going to be the equation y equals to a over b, where a and b are the leading coefficients. So simply dividing whatever these 2 numbers are. For example, look at example 1. We're going to write the horizontal isotope and then write a limit statement to describe the end behavior. So on example 1a, this is an example of this case 1. Our leading terms are 2x to the third. I meant to get the highlighter. 2x to the third and 6x to the third. And it's not because, again, they're in the front, which I know there are, okay, but because the exponent is the biggest. So in the case where these numbers are written in a different order, and this one is maybe somewhere back there, this one's still going to be the leading term because it should technically be in the front because of the highest degree, okay? So these problems, again, are set up where this number is already in the front. But if it's not, again, you would just simply look for it. So since those numbers, again, terms, I'm sorry, are already in the front, there's our leading terms. Looking at these exponents, since these exponents are the same, then the equation to the horizontal isotope, which I'll abbreviate like this, is the equation y is equal to the 2 over 6, simply dividing the leading coefficients, which reduces to 1/3. So this is a boundary line. So because of this boundary line, the graph is going to be a rational function, and I'm just going to draw a rough sketch of this, okay? This is not going to be accurate. There's going to be a horizontal boundary line right here at y is equal to 1/3, where the left end and the right end are going to simply get closer to. So the y values are going to get close to that value on the very far left and on the very far right, which means the way we describe the end behaviors using limit notations is that the limit as x approaches both positive and negative infinity is simply going to equal to 1/3. So this is a statement that describes the end behavior of this rational function. All right. Now the second case is if they're not the same, well, one would have to be bigger than the other. Well, if the denominator dominates the numerator, which simply means that the exponent on the top is smaller than the exponent on the bottom, then your horizontal isotope is simply going to be the equation y is equal to 0 every single time. Taking case again, taking case example B here, 1b. Notice again that the leading terms are already set up for us. They're already in the front. And the exponent in the numerator, 2, is smaller than the exponent in the denominator, 3. So the horizontal isotope, this is case 2, is going to equal to 0. So that's your horizontal isotope. And therefore, the statement, the limit notation statement that describes the end behavior would be that the limit as x approaches negative infinity of g of x is 0, and the limit as x approaches positive infinity to g of x is also going to equal to 0. And there, that is your answer. Now, the third case won't talk right now about it right now in the next page, okay? So we let's postpone this one for right now, okay? But this last case simply states if it's the other direction. If the numerator dominates the denominator, okay, it is not going to have a horizontal isotope, but instead the end behaviors are going to behave again to what the equation to this ratio will be, okay? It will be a over b, but you'll have to subtract this to see what that's going to look like. And we'll talk about that in the next page. So let's look at 2 more examples that are relative to case 1 and case 2. So for letter 1C, let's look at this, okay? Well, this is going to be another case 1 scenario because the leading terms both have a degree of 3 and 3. So this would be case 1, where I simply have to divide those leading coefficients. So I take this coefficient of negative 3 and put it over the coefficient of 1, and that's going to be negative 3. So that's my horizontal isotope, y equals negative 3. So the limit statement that describes, again, the end behaviors of h are these. Moving on to the next example. Well, right here, we can determine again which case we have, 1 or 2, or even a third one, because this is not in its polynomial form, it's in the factored form. So we need to figure out what the leading term or terms are going to be. What's the leading term in the numerator going to be, and what's the leading term in the denominator? Okay. So we need again, we need to figure out what b and d, a and n are going to equal, and b and d are going to equal to. So for the top, to figure out the value of a, that's just simply multiplying all the leading coefficients. So we're going to multiply 1, 1, and negative 2 together, and that's going to be a total of negative 2. And to figure out the value of n, the degree, we add up all the linear factors. So 3 plus 1, and well, this one doesn't have an x, so we don't add anything right there because this is x is 0. So 1 plus 3 is 4. And now the same thing for the bottom. To figure out the value of b, the leading coefficient, we multiply all these coefficients. So 1 times 1, that's going to be a total of 1. And to figure out the degree, we add up the linear factors. So 3 of x to the zeros and 2 of x equals to 3. So that's a total of 5. And there. And this is going to be case 2. The degree of the top is bigger than the degree on the bottom. So this is case 2, which means that the horizontal isotope is y is equal to 0. So let's write our statements here. And there you have it. This is the end behavior of this rational function r. Okay. Let's move on to now to the next page. And finally, on our last page, we can now talk about case 3. And we're going to talk about a very specific situation with case 3, where the numerator on the top is bigger than the numerator on the bottom, that's going to create an asymptote. It's not going to be horizontal though, but it does create an asymptote where the end behaviors are going to behave again to this equation right there. And we're going to focus on where the degree of the numerator is only specifically 1 unit higher than the degree of the denominator, okay? Only in that case right there. If that's the case, and we have that special situation where the degree of the numerator is exactly 1 unit greater than the degree of the denominator, then the rational function is going to have instead a slant asymptote that's going to be parallel to the ratio of the leading coefficients, to these values right there. So if this number is bigger than that number by 1 unit, okay, then the function is going to have a slant asymptote, so a line that's slanted, y equals mx plus b, where the slope of the line is going to be parallel to this ratio right here, a over b. So look at this picture right here. This function is represented by this portion of the graph, okay? This is f of x. Notice that the degree up here, 2, is 1 unit higher than the degree down there, 1. Because of this, instead of having a horizontal asymptote, we have a slant asymptote. There we go. That moves upwards, and the equation of this slant asymptote is this equation right there, okay? Notice that this equation, 3 over 2x plus 9, focus on this part right there, okay? This number right there, 3 over 2x, which is the slope of this line, corresponds to these numbers right there. So while we won't be able to come up with what the equation of the line is, at least right now, not right now, we can identify the line that's going to be parallel to this right there by simply dividing these two quantities. And with that, by noticing that the slant asymptote has this slope, or is going to be parallel to this line right here, okay? That's going to be parallel to this line right here with this positive slope, we can identify the end behaviors of f by understanding again the behavior of a line. Since this line is positive, the left side of a positive 9 is always pointing downwards. So the left end behavior is going to approach negative infinity. So this rational function has no boundary line, so it's going to behave almost exactly like a polynomial function where the ends are going to be pointing in opposite directions, okay? One end is going to point up and the other end is going to point down. So with rational functions, again, that are unbounded, the two ends always pointing opposite directions. So this end right here, well, when it has a slant asymptote, okay, slant asymptote, this is going to approach positive infinity, the right end. Okay. So let me highlight them. So this is referring to this end over here, and this, the right end, is referring to that one. So even though we don't have a boundary line to say that our rational function is getting close to that boundary line, with a slant asymptote, we can simply look at what the slope is, and because of that slope being, well, either positive or negative, we know how the graph, the ends are going to behave, because lines, again, move in one straight direction diagonally. Okay, well, these type of lines move in a diagonal direction. And if this number was negative, then the line would be going like this, and this would just be backwards. The left end would be pointing upwards, and the right end would be pointing downwards. Now, before we look at examples of that, let's look at this example. Well, you know what? Let's do examples like that. Let's skip example number 2 right now, and let's go to example number 3. Let's determine the equation that is going to be parallel to the slant asymptote, then write a limit statement to describe the end behavior of each rational function. Now, in order to have a slant asymptote, remember, this number has to be bigger than that by a unit of 1. And obviously, these are going to be set up exactly for that situation. So this number 2 is bigger than that number by a unit of 1. So that means that the slant isotope, I'll call it slant, all right? Our slant isotope is going to be the equation y is equal to 3 over 1x, or simply y is equal to 3x, okay? So that is the equation that's going to be parallel. This is not the slant isotope, okay? This is not the equation of the slant isotope, but this is the equation of the line that's going to be parallel to the slant isotope. So this equation is going to be parallel to whatever the slant isotope is. Okay? Now, to figure out what the end behaviors are to F, they're not going to equal to a number because we don't have a horizontal isotope, we have a slant. Well, since this line is positive, positive lines look like that. So the left end of the graph is pointing towards negative infinity, and the right end of the graph is going to point to positive infinity. Okay, whether it's from below and this one is above, or they're both from above, or they're both from below, the ends of the graph again of this rational function are going to be again getting closer and closer to this line right there. Okay, now while we don't know what the y-intercept is, we know it's going to be parallel to this, and since parallel lines move in the same direction, okay, they don't intersect, then we know it's going to look exactly the same. I'm sorry, behave, not look exactly, but behave exactly the same. So let's look at example B, okay? Example B, same scenario here. This is set up again for the degrees to be 1 unit higher, as you see right there. X to the third, x to the second, that's 1 degree higher. So this thing has a slant isotope and not a horizontal isotope. And the equation of the slant isotope is y is equal to 1x. And 1 because it's 1 divided by 1, so 1x. So the end behaviors, the limit notation that describes the end behaviors will be that the limit as x approaches negative infinity of g of x is going to be the same as the previous example. And again, the reason for that is because the slope of this line is positive 1. So the left end is going to be pointing downward and the right end is going to be pointing upwards. Now, had it been negative, let me do another example. Okay, let's call this C. We'll call it h of x is equal to, I'm just going to switch the signs on the top. Negative x to the third plus 2x squared minus 6x plus 9. And on the bottom is going to be the same. X squared plus 2x plus 3. Had the equation been like this, then the slant isotope would be y is equal to negative 1x. And well, since our slant isotope is going to have a negative, well, it's going to be parallel to this first of all, right? This is not, again, not the equation. This is not the equation of the slant isotope. This is just the equation of the slant isotope that's going to be parallel to the actual slant isotope. But because they're parallel, they're going to both have a slope of negative 1, which means that the graph, the slant isotope is going to be going downwards, whether the y-intercept is there or the y-intercept is down here. This line has a negative slope, so whatever the slant isotope is to this, it's going to have that exact same slant, the same slope of negative 1. So that means that the left end is going to be pointing upwards, negative infinity. So this will be negative infinity, and the right end is going to be pointing downwards, so that's going to be positive infinity. Okay. And for right now, if this is not the case, if the difference in the degree of the numerator and the denominator from the denominator is not 1, then we'll say that it has no asymptotes for right now, okay? Slant or horizontal. So let's look at the next example 2, all right? For example 2, we want to find out which of the following rational functions has a slant asymptote that's going to be parallel to y equals to 1 over 2x, okay? Well, two things that we need to recognize here. First of all, is that in order to have a slant asymptote, to have a slant asymptote, the degree of the numerator has to be bigger than the degree of the denominator by 1 unit, okay? So n has to equal to whatever d is plus 1 more, okay? So that's exactly what we need to look for first. So that eliminates the first one because those degrees are the same. Let me zoom in here. Those degrees right here are both the same, so this one is out. These ones are not the same, but it's in the opposite order. We need this number up here to be bigger than the one on the bottom, so this one is out. So that leaves us these last two. Well, let's talk about the last one first. The last one doesn't work because even though this one is bigger than that one, the difference between those two numbers is not 1. 4 minus 2 is 2. So this has to be a difference of 1 unit. So this one cannot be it. So the correct answer has to be this one right here, that when I figure out what the horizontal asymptote, the slant asymptote to this, when I figure out what the slant asymptote to this is, it should be parallel again to 1 over 2. And let's see what it is. Well, if I get 1 and divide it by 2, that's exactly it. The equation to the slant asymptote right here would be 1 over 2x plus some value of b, okay? We don't know what that y-intercept is, but we'll know we have a y-intercept. And since this number matches the slope to this one right there, this is the one that would have to be parallel. This is the one that would have a slant that's going to be parallel to this equation right there. So there's your answer. Okay, so slant asymptotes again, the end behaviors of a rational function with a slant asymptote will be very similar again to the direction of our line. If our line is positive, then the left end is always pointing downwards and the right end is pointing upwards. But if our slope to our slant is negative, then the behavior of our function would be opposite. This would point upwards, so this will be positive. This would be positive, sorry. And on the right end, this would be pointing downwards, so this number should be negative infinity. Well, that concludes again our notes on 1.7. If you have any questions, please send me a message. And like always, I appreciate you watching and I hope you have a good day. Goodbye.